Welcome you all to session 3 of the chapter Motion in a Straight Line. In this session, we will be learning about velocity time graph and its applications. A graphical representation is a convenient form to describe a motion. Okay, let us study about velocity time graph. It is a graph in which velocity of a body is plotted along y-axis and time is plotted along x-axis. So that kind of graph is called as velocity time graph. Okay, what is velocity time graph? Let us take, it is a graph in which velocity of an object is plotted along y-axis and time is plotted along x-axis. Okay, a graph in which velocity is plotted along y-axis and time is plotted along x-axis, that graph is called velocity time graph. That kind of graph is called as velocity time graph, or it is also called as VT graph here, right? So in short, we can write it as VT graph. Okay, let me draw velocity time graph, then you will come to know here, right? Okay, now let us take a graph, right? This graph consists of x-axis and y-axis, right? The velocity of the object is plotted along y-axis and time is plotted along x-axis. Let me take the body moves like this now here. What is the meaning of this? Let us understand. How to read the graph? Let us understand here, right? Here, the time, what happens to the speed of the body, what happens to the velocity of the body as the time passes? Of course, time will change now, right? Time means changing at every instant, right? As the time passes, what happens to the velocity? The velocity of the body. In this graph, we can understand that as the time passes, velocity is increasing, right? The velocity is increasing continuously, right? So that is how the motion is here, right? So this is a graph which gives the idea that how actually the body is moving, right? As time passes, the velocity of the vehicle or the velocity of the body increases continuously. Means if a rider is riding a bike, he is riding in such a way that continuously he is increasing the speed of the vehicle. That time, if I draw the velocity time graph of that bike now here, I will be getting like this. By seeing this, I can understand that, okay, the velocity is increasing now here, right? Okay, so this is called as velocity time graph, right? Okay, what is its importance? Let us check it out now here, right? If you take a graph, we can draw a triangle to it. Let me name it as A, let me take it as B, and we can take it as C, right? So we can calculate the slope of a line here, right? You are straight about this. How to calculate the slope, right? Okay, you know how to calculate the slope? The slope of a line is given by, right? So in order to calculate the slope of the line, right, slope of this VT graph, I need to take a triangle here, right? So triangle may be of any size now here. You can take here or you can take a bigger triangle. It does not make any difference in the slope, right? Okay, let me take a graph. So I got a triangle here, A, B, C. You know how to calculate slope? Slope can be calculated by y-axis divided by x-axis. So what is y here in this triangle here? Y is AB. AB divided by what we say here? CB. Y by x gives what we say here? Slope, right? You know how to calculate slope? This is y and this is x. We can calculate the slope now, right? Okay, now in this graph, what is y? Let us check it out. In this graph, what is y now here? This y is nothing but this much, right? What is this? Change in velocity. Yes. What is this? AB represents in this graph change in velocity, right? Shall I say change in velocity? Let me write it as dv, small change in velocity, right? Okay, what is CB in this graph? In this graph, what is CB? That is change in time, right? How to represent the change in time? Let me take it as dt, right? So what does slope gives? That is dv divided by dt, right? So what is the dv by dt? We have studied in the last session differentiation of velocity. What is differentiation of velocity? Acceleration, right? We have studied it. Change in velocity with respect to time is called as what we say here? Acceleration. What does the slope of vt graph gives? Slope of velocity time graph gives acceleration. You need to understand this. So what does slope of velocity vt graph, right? So what does slope of vt graph gives? Slope of vt graph gives what we say here? Acceleration. It gives acceleration, right? It can be asked for one more question. What does slope of velocity time graph gives? Okay, slope of velocity time graph always gives what we say here? Acceleration, right? If you calculate the slope, you will come to know that change in velocity divided by time taken, it is nothing but what here? Acceleration. So this is one of the important factor of vt graph. Means when you draw vt graph, if you take the slope of that, you will be getting the acceleration, right? So that is the use of vt graph now here, right? Okay, now let us take some more vt graphs now here. Let me take vt graphs and you need to analyze that, right? So one of the significance of vt graph is slope of vt graph gives acceleration. Now let us take some examples now here, right? If I'm writing like this, let me draw vt graph here. This is velocity and this is time. This is vt graph, right? Okay, let me draw the vt graph and let us analyze what is happening now here, right? Okay, so let me take now here like this. What is the meaning of this? How actually the body is moving now here, right? As time passes, right? As the time passes, what is happening to the speed of the vehicle? What is happening to the velocity of the body? Velocity of the body is not changing at all. It remains the same. Means the body is moving with a uniform motion, right? Okay, see here. This graph gives the idea that body is body moving with what we say here? Uniform motion or uniform what we say here? Velocity, right? So the body is moving with uniform velocity or uniform motion here, right? Okay, so body is moving with uniform velocity. So this is the graph now here, right? Okay, just to analyze the graph, what is happening here, right? So I took a vt graph and I took the graph like this. As the time passes, what is happening to the velocity? See, imagine there is a bike rider now here. The velocity, he is keeping the same now here, right? It is not changing at all. If he is riding with 50 km per hour, he is keeping at 50 km per hour itself. Throughout his journey, he is not increasing the speed or he is not decreasing the speed. He is keeping constant. If he keeps constant, the body is moving with uniform motion or body is moving with uniform velocity. What is the meaning of uniform? Uniform means same. Right? In this graph, it says that the body is moving with the same velocity, or if the body is moving with same velocity, so then that kind of motion is called as uniform motion, right? So this is the VT graph. So in the examination, the question may be asked like this: draw VT graph for uniform motion. So this is the thing, right? Draw VT graph for a body moving with uniform motion. So this is the graph now here, right? Okay, let me take another one graph now here. So this is, let me take, this is velocity along y-axis, time along x-axis. So let me take like this. So this is along x-axis, and let me take the graph like this. What is the meaning of this? How actually the body is moving? This already I took earlier, right? Here the body is moving with increasing velocity, right? Okay, so let me take now here. Body is moving with, right? Moving with uniform acceleration. See, a body is moving with uniform acceleration. Exactly, right? As the time passes, what is happening now here? Velocity is increasing. Earlier, what was the velocity? Zero. Right? Suddenly velocity increases and it is increasing continuously throughout the motion. Means, just imagine there is a bike rider, he is at rest now here. He is increasing continuously. What means, what is giving to his bike? He is giving acceleration. How is the body is moving? Body is moving with uniform acceleration, right? It is in a straight line, right? That we call it as uniform acceleration. So this is a graph of VT graph with the body moving with uniform acceleration, right? Means the velocity is increasing continuously, right? If velocity is increasing continuously, we can call that kind of motion as accelerated motion here, right? Okay, now let me take another one graph here. So this is the velocity along y-axis and time along x-axis. Let me take graph like this. What is the meaning of this? Just analyze the graph now here, right? As the time passes, velocity decreases continuously. Means he is already moving with a high speed now here, right? He is decreasing the velocity, right? He is decreasing the velocity means acceleration is negative, right? Okay. So here, shall I say like this? Body is moving with uniform. He is decreasing the speed. He is decreasing the speed. If he is increases, let me call it as acceleration. If he is decreasing, let me call it as retardation. I already told about this, right? Negative acceleration is called as retardation, right? We are studying in the last session that acceleration is positive if velocity is increasing, right? Acceleration is negative if velocity is decreasing. Acceleration is zero if velocity is zero or velocity is constant. That we have seen in the last session. Similar, let me tell that in graphically now, right? So what is happening now here? Velocity is decreasing, means he is decreasing the velocity, means body is moving with the uniform retardation, right? Okay, let me take another one graph now here. This is the velocity time graph. Here let me take velocity and let me take time here, right? Okay. Now, if I'm calculating velocity time graph and the graph is like this now here, right? What is the meaning of this? Right? Here actually the body is moving now here, right? So body moving with, okay, just analyze what is happening. First, as time passes, first the velocity increases, then velocity decreases, again velocity increases, again velocity decreases, means the body is moving like this. Okay, he is riding a bike now here, he increases, suddenly he finds a road breaker, he decreases the speed, again he increases, again he decreases. Usually the whatever we find the motion in day-to-day life is like this itself, right? So what is happening to the velocity? Is it same? No, it is changing. If it is changing, shall I call like this? It is the body is moving with variable, what we say here, velocity. Body is moving with variable velocity, means it is the velocity is changing continuously, right? So once time it is increasing, once it is decreasing, right? Let me call it as variable, right? So this is a graph which represents body moving with variable velocity. So these are some of the typical graphs of velocity time graph now here, right? One significance is the slope of velocity time graph gives acceleration. Let us see what is the second significance of velocity time graph. Now let us find what does area under velocity time graph gives. Okay, let us take velocity time graph now here. We know that a graph in which velocity is plotted along y-axis and the time is plotted along x-axis is called as velocity time graph. Okay, let me take a situation, right? Okay, let me take like this. What is this motion? How is this motion here, right? This is velocity time graph gives, right? Okay, come on, tell me how actually the body is moving. As time passes, velocity is not changing at all. Means a body is moving with a constant velocity. Let me take. Consider a body. Consider a body moving with what we say here, constant, or it is also called as uniform velocity. Velocity is not changing at all, right? That case I took and I will be calculating what is the area under VT graph gives in here, right? Okay, now consider a body moving with uniform velocity. So this is the case now here, right? So I need to find what is area under VT graph gives, right? So I will be calculating what is area under VT graph gives. What is VT graph? This is the VT graph, right? So what is the area under VT graph? Shall I take like this? This is dotted line. What is the area under VT graph? So this is the area under VT graph, right? Let me take this is O, let me take this is A, let me take B, and let me take it as C here, right? Okay, now what does this area under VT graph gives? Right? Is it a rectangle? Yes. How to find the area? Length into breadth. Means shall I say like this? OA into OC gives area under VT graph, right? Okay. So area under VT graph is nothing but area of, which is that area? OABC. OABC. That is area under VT graph, right? How to calculate OABC? OABC is a rectangle. So you know how to calculate the area, length into breadth. OA into OC. Shall I write here? Right. So area of OABC is OA into what we said here? OC. OA into OC. What is OA? OA is nothing but it is nothing but what now here? Velocity, right? OC. What is OC now here? It is nothing but what now here? Time. What is velocity into time? We know that. What is the formula for velocity? Velocity is displacement divided by time taken, right? Displacement divided by time taken is velocity. What is velocity into time? If you bring time this side, what does it give now here? It is displacement. So velocity into time is nothing but what we say here? Displacement. Velocity into time is displacement. So what does area under VT graph gives? Area under VT graph gives displacement. So I write like this. Area under VT graph gives displacement. So this is another one significance of VT graph. Okay, earlier I proved that slope of VT graph gives acceleration. In the similar manner, area under VT graph gives what we say here? Displacement. Right? One more question. What does area under VT graph gives here? That is displacement, and I have proved this. The question may be asked like this also. Show that area under VT graph is equal to displacement. Just I proved that area under VT graph is equal to displacement. Right? So this is the proof for area under VT graph gives displacement, considering the case that a body is moving in a uniform velocity. Right? Okay. Now, let me take what are the applications of VT graph. We already studied what actually the VT graph is, and we took some cases. Now, let us check it out. What are the uses of VT graph? What are the uses of VT graph here, right? So what are the uses of VT graph? Let us take velocity time graph is used, right? Okay, let us take. It is used to describe the nature of motion of a body. Right? Already told you, VT graph is used to describe the nature of motion of the body. How actually the body is moving, right? Is it increasing its speed, or is it decreasing the speed, or is it keeping the same speed, or it is changing continuously, right? To describe the nature of motion of a body, this VT graph is used here, right? So VT graph is used to describe the nature of motion of the body, right? So it is used to measure velocity. It is used to measure velocity at any instant of time. At any instant of what we said here? Time. So it is used to measure velocity at any instant of time, or in short, shall I say like this? It is used to measure instantaneous velocity. Let us consider a graph like this. So this is a VT graph, and if I am taking, this is the kind of motion. If I want to find what is the velocity at this time, can I find? Yes, I will be getting this, right? At any instant of time, you can find the velocity, right? To measure velocity at any instant of time. For example, if I want to find what is the velocity at this time here, right? So you can find like this, right? So by using VT graph, you can find velocity at any instant of time, right? Okay, now let us go with the third one. It is used to calculate acceleration of the body. It is used to calculate acceleration of the body. Yes. How to calculate acceleration of the body? Take the slope of VT graph. Yes. If you take the slope of VT graph, you will be getting acceleration, right? Okay. The next use is to calculate displacement of the body. To calculate displacement of the body in the motion, right? To calculate displacement of the body. How to calculate displacement? Take the area under VT graph, right? Area under VT graph gives displacement of the body. So these are some of the uses of VT graph. Now let us move ahead here, right? Let me take kinematic equations and let me derive those equations using VT graph. Right, kinematic equations for uniformly accelerated motion. Okay, the next concept is about kinematic equations. Kinematic equations for uniformly accelerated motion. Uniformly accelerated motion means the acceleration of the body remains constant throughout the motion. Then that kind of motion is called as uniformly accelerated motion, right? So we have kinematic equations for uniformly accelerated motion. There are three kinematic equations. There are three kinematic equations. Kinematic equations for uniformly accelerated motion. Do remember, for uniformly accelerated motion means it is a motion in which acceleration remains constant. If this is the case, then we have three kinematic equations. The first one is v is equal to u plus at. Second one is s equal to ut plus half at square, right? And the third one is v square is equal to u square plus 2as. So these are what we say here, 2as. So these are three equations which are called as kinematic equations, and these three equations can be applied only when acceleration remains constant in a motion. Then only you can apply these three equations. So these three equations are called as kinematic equations, and we will be deriving these three equations using VT graph. Okay, let me begin with the first one, that is derivation of v is equal to u plus at using VT graph. Now let me draw VT graph for uniformly accelerated motion. Means a body is moving with uniform acceleration. Okay, let us take a VT graph for that now here. This is VT graph. Velocity is plotted along y-axis and time is plotted along x-axis. So velocity along y-axis and time is plotted along x-axis. And uniformly accelerated motion, let me draw the graph like this. This is uniformly accelerated motion. Means the acceleration remains constant, means change of velocity with respect to time remains constant, means you will be getting a straight line like this. Okay, let me write about this. Consider a body moving with uniform acceleration. Consider a body moving with uniform acceleration. Do remember, whenever a body is moving with uniform acceleration, then only kinematic equations can be applied, and we are deriving first kinematic equation, that is v is equal to u plus at. Okay, consider a body moving with uniform acceleration. Let u be initial velocity. Let me call u as initial velocity. Let u be initial velocity and v be final velocity. V be final velocity after time t. After time t. Right? Okay, see here. Let the initial velocity be u and final velocity be v after time t. Right? Okay. This is velocity. Let me call it as O now here. Let me call this as A and let me call this as B now here. Right? So which is the initial velocity? This is the initial velocity, right? From here the body begins to move now here, right? So this is the initial velocity which I am considering. So OA is the initial velocity. Shall I say OA is the initial velocity and we denote it by U. This is the final velocity. Okay, this is the final velocity, right? After time t, let me take like this now here. After the time t, this is the time t. After time t, velocity increases to final velocity. Means what is this now here? Let me call OB. Let me call it as C. What is BC? BC is final velocity. Let me call it as V, right? So do remember here, y-axis we are plotting velocity. Means what is OA? That is initial velocity, and what is BC? That is final velocity. After time t, let me call OC as time t, right? This is the time t now here, right? After time t, velocity increases from U to V. Shall I take like this, right? Okay, now let me continue with the mathematical form now here, right? For instance, let me make certain construction here. Let me draw a perpendicular line and let me name it as D now here, right? Okay, now let me prove now here. What we are doing, we are calculating V is equal to U plus AT, right? Here we have V, U, we have T, we don't have A. What is A? Acceleration. What does acceleration in the graph gives now here, right? So the slope of the graph gives what we say now here, acceleration. So let me make use of VT graph. Using VT graph, right? Let me make use of VT graph. Okay, in the VT graph, we know that slope of slope of VT graph gives what we say here, acceleration, right? Slope of VT graph is nothing but, what is slope of VT graph? So what is VT graph here? Slope of AB, right? It is nothing but slope of line. What is that line here? That is AB, slope of line AB. We have already studied how to calculate the slope of this. Take a triangle here. Already there is one triangle. Let me make use of that itself, right? There is already triangle, which is a triangle ABD. This is already, we have the triangle, right? Do you understand? Let me draw it later. For understanding sake, let me take this. This is a triangle, right? How to find the slope of this line? Slope of the line is given by y by x. Y-axis divided by x-axis. What is y here? Y is BD. That is equal to BD divided by x-axis. What is x-axis now here? AD. Shall I take now here? BD divided by AG. Right? Okay. Now, but what is BD? We don't know. What is OA? Yes, we know what is OA, initial velocity. What is BC or CB now here? That is final velocity. But we don't know what is BD now here, right? So what we want BD. Can I share like this now? How to write BD? BD can be written as, here, just imagine this. I want this distance. What is BD? Can be written as BC minus DC. Shall I say like this? BC minus DC gives what we say here, BD. Okay, instead of BD, let me write what we say here, BC minus what we say here, DC. BC minus DC gives what we say, BD, right? Okay, now divided by what we have now here, AD. So what is that now here, AD? Shall I write like this? Come on, tell me, what is BC then? What is BC? Where is BC? This is BC. What is this? This is nothing but water. Final velocity. Shall I substitute there? Right. So what is this now here? It is final velocity minus. What is DC? Just check it out. In the graph, what is DC? DC. This DC is nothing but AO. Right. This length is nothing but this length. So I am drawing a straight line here. If I draw the straight line, this DC is equal to what we say now here, AO. What is AO, man? AO is nothing but water, initial velocity. So shall I take it as U? Yes, U divided by. What is AD? AD. AD is nothing but water. OC. Yes. AD is equal to OC. We know what is OC. OC is the time T. Shall I write here? In place of AD, let me take time T. Okay, come on, tell me, what does slope of VT graph gives? Slope of VT graph gives acceleration. That is the significance of VT graph now, right? So this gives what now here? Acceleration. Shall I bring a T to this side? What do you get? AT is equal to V minus U, right? So that implies V equal to, if I bring minus U to this side, it will become plus U, right? V is equal to U plus AT. So this is the derivation, right? So derive U is equal to, so V is equal to U plus AT using VT graph. So I have made use of this VT graph and derived this, right? Do you remember? Derivation starts like this. Slope of VT graph is nothing but slope of the line AB. How to get the slope? Y-axis divided by x-axis. What is y-axis? BD divided by AD. So we have calculated. What is BD? We don't know actually what is BD. So BD can be written as BC minus DC, right? So BC minus DC, we know all these things, right? BC is nothing but final velocity. What is DC? It is nothing but AO, that is initial velocity. What is AD? Is nothing but OC, that is time now here. After substituting, we got the equation V is equal to U plus AT. Remember, these are important derivations, right? One among these three derivations will be asked in the examination. Derive V is equal to U plus AT. If the question is asked, so this is the answer. Now, let me move on to the second kinematic equation, that is S equal to UT plus half AT square, and we will be deriving this by using VT graph now here. Velocity time graph remains the same for the second derivation, right? This is the derivation, second derivation, that is derivation of S equal to UT plus half AT square using VT graph. So this is one of the important questions that can be asked for 5 marks, right? Derive S equal to UT plus half AT square using VT graph, right? I already told you these equations can be derived only when a body is moving with uniform acceleration. So this is the graph, and OA is the initial velocity, and BC is the final velocity after time T, that is OC. So these all things we know now here, right? From this, let me continue how to derive. Okay, now let me make use of this VT graph. From VT graph, right? So from VT graph, what I need the derivation for displacement. You know, displacement. So in VT graph, what gives the displacement? Area under VT graph gives displacement. Yes. Okay. Let me continue with that now here. Right. I want a displacement. So let me take now here what gives displacement. Displacement is equal to area under which graph? VT graph, right? Area under VT graph gives displacement, right? We know area under VT graph gives displacement. What is that area? So this is the area, right? Area under VT graph. So which is that area now here? This is the area. This gives displacement, right? Okay, now this area, shall I divide into two parts? For simplification, let me divide into two parts. One, area of this triangle. Let me take, this is the one triangle and this is a rectangle. Let me divide like this, right? So what is the area under VT graph? Let me first write what is area under VT graph. That is area of, what is the area of? OABC, right? OABC, right? OABC. This is the area under VT graph which gives displacement. Now I will be dividing it. Okay, let me divide into two. One is triangle and another one is rectangle. Let me take this. That is equal to area of triangle. Let me take area of triangle. Which is that triangle? ABD. Area of triangle ABD. This is ABD, right? So plus area of rectangle, right? Shall I say like this? That is area of rectangle. So what is that rectangle? OADC. OADC, right? Okay, area of OABC can be divided into two parts. One, area of triangle ABD and another one, area of rectangle OADC. So this two we will be adding. We know what is the formula for triangle? The formula for area of triangle is half into L into breadth, right? Half into length into breadth. Okay, let me take that. That is equal to half into, where is that? ABD. Here there is ABD in here, right? Okay, so what is the area of triangle ABD? That is half into length into breadth. That is half into BD into AD. Shall I write like this? Half into BD into what we say now here? AD, right? Plus, let me write plus like this. Half into length into breadth. Half into BD into AD, right? Now, what is area of rectangle OADC? OADC. This is rectangle. What is the area of the rectangle? Length into breadth, right? Shall I say length into breadth? That is OA into OC, right? Okay. What is area of rectangle? That is OA into what we say now here? OC. Shall I say like this? Right? Okay. Now this can be written as that is equal to half. What is BD? Come on, tell me. What is BD? Where is BD? Here there is BD. We know from last derivation. What is BD can be written as BC minus DC, right? So what is this? This is nothing but what now here? U. What is BC? That is V now here, right? So then what is BD? V minus U, right? BC minus DC can be written as V minus U. So what is this BD? Do you understand? This is U and this is V. What is BD? BD is V minus U. Shall I say like this? This is V minus U. What is AD, man? Where is AD? Here there is AD. Okay. Shall I remove this? Okay. Now, what is AD? AD is nothing but what? OC. It is nothing but what now here? Time. Right? We know OC is time. So, AD in place of AT, shall I take it as time t? Right? AD is equal to OC. That is equal to time t now here. Right? Okay. Plus. What is OA? Just think it out. What is OA? Where is OA? Here there is OA. What is the OA? Initial velocity, right? So let me take now here initial velocity U into, right? What is OC? Where is OC now here, right? OC. OC is nothing but what? Time, right? We know OC is nothing but what? Time t. Shall I do this? Right? Okay. That is equal to half. What is V minus U? Right? We know that V is equal to U plus ET. That we have derived. First kinematic equation, V is equal to U plus AT. What we want? V minus U. Shall I bring this U to this side? V minus u. What do you get now here? Et, right? Okay, I just bring this u to this side. It will become v minus u. That is equal to at. Shall I substitute that at here? Right? Instead of, let me substitute here at. So what do you get now here? At into t plus u into t. Shall I say ut? So what do you get now here? That is equal to half a t into t square plus ut. Come on, tell me, what is this? Displacement. Displacement, it is denoted by S. Did we get the equation? Yes. This equation can be written like this also. S equal to ut plus half at square. S equal to ut plus half at square. So this is the proof, right? I have proved the second one. S equal to ut plus half at square using VT graph, right? Taking VT graph, just we proved how did we get S equal to ut plus half at square, and this is the second derivation, right? So we proved v equal to u plus at, and we also proved S equal to ut plus half at square. Remaining is third one that we will be proving. Third one, v square is equal to u square plus 2as. Let me derive that also by using VT graph. Consider a body moving with uniform acceleration, right? Considering this case, I will be deriving v square is equal to u square plus 2as using VT graph, right? Where u is the initial velocity, v is the final velocity, and time taken is t now here, right? So this is initial velocity, this is final velocity, and this is the time I have written here. Okay, let me continue here. So we are finding v square is equal to u square plus 2as. So let me use this now here, right? From VT graph, let me use this VT graph and calculate this derivation now here, right? Okay, from VT graph, shall I take now here displacement? Okay, first of all, what will in VT graph gives displacement of a body, right? Is area under VT graph. We know area under VT graph gives displacement, that is area under VT graph. What is that VT graph right here? AB is the VT graph, right? Area under AB, right? Area under AB gives what we say right here? Displacement. As this equation has the displacement, I have taken that and I will be proving it now, right? So displacement equal to area under AB, right? So what is area under VT graph? That is area under AB. What is area under AB? So this is the area, I already told you. So this is the area, right? Let me take, this is the area, right? In the last derivation, I took this area as two parts, triangle and rectangle. Let me not take here, let me take directly the area itself, which is that area OABC. This is OA, the diagram is like this, just see here. This is OA, B, and also what we say here? C, right? Do you know which quadrilateral it is? It is trapezium. You know, trapezium is a quadrilateral which has four sides, where one of the opposite sides are parallel. If it is like this, then this kind of diagram is called as trapezium, right? Let me make use of that now, right? We have the formula for area of trapezium. Let me make use of that and let me prove this, right? Okay, what is area under AB? Area under AB is, shall I say like this? This is area of trapezium, trapezium. Which is a trapezium? OABC, OABC, right? Area of trapezium, OABC, right? You know, what is the formula for area of trapezium? The area of trapezium is half into sum of parallel sides, sum of parallel sides into, right, into base. So this is the formula, right? Sum of parallel sides, this is A and this is B. That is, the formula is half into A plus B into the base. If I'm taking, this is the base now here, so into what we say here, base. That is the formula, right? Okay, sum of parallel sides into base. Let me use that formula here. That is equal to half into sum of parallel sides. Which are the parallel sides here? AO and BC are the parallel sides. Let me make use of that now here, right? Let me take the sum of that. That is AO plus what we say now here? BC. AO plus BC, sum of parallel sides, into what is base? So this is the base. What is that base now here? OC. Let me write here, right? Here base is what we say OC. Now let me take what actually these are. That is equal to half, right, into bracket. What is AO man? AO, what is this? Initial velocity, right? AO is nothing but initial velocity u. plus, come on, tell me what is BC? Where is BC? BC. This is nothing but water. Final velocity, right? So BC, it is nothing but final velocity. Into, what is OC, man? OC is nothing but water. Time, right? OC is time. So what shall I take now here? That is T, right? Okay, now let me make use of this formula, that is U plus V. I want a time, but we already have the formula for a first kinematic equation, that is V is equal to U plus Et. Shall I make use of this? And let me substitute here, right? I want a time. Shall I bring V to this side? What will come? V minus U is equal to, what we say here? At. I want a T. What shall I do now here? Shall I bring this A to the denominator? So that is equal to, what do you get now here? T, right? So from that equation, we got T is equal to V minus U divided by A. Let me substitute here, right? In place of T, let me write V minus U divided by A. Shall I write like this? Yes. Now, we have, so let me continue now here, right? So if you see this, just observe that. That is equal to half, what is this? U plus V, and what is this now here? V minus U. Is it similar to A plus B, A minus B? Yes. What is the formula for A plus B into A minus B? A plus B into A minus B is A square minus B square, right? It is similar to A plus B, A minus B. Means V square minus U square. Shall I substitute here? That is equal to V square minus U square, right? So how did you get this? By using the identity A plus B into A minus B is equal to A square minus B square, right? So this is A minus B, this is A plus B, right? So that is why V square minus U square. Be careful here, right? So here this is V minus U. That is why I have taken it as V square minus U square. It is not U minus V, right? So U plus V or V plus U, both are nothing but the same, right? So just take it out, U plus V plus U here, V minus U there. So V plus U, V minus U is equal to V square minus U square. So just I have taken that. What is remaining in the denominator now here? A. Shall I take this A here? This is denominator A. So what is this now here? Displacement. What is this? Displacement. Displacement is denoted by yes, right? Shall I take here yes now here? Now let me bring this 2A also here. What do you get now? 2A yes is equal to V square minus U square, right? Shall I bring U square to this side? What do you get? V square is equal to, if I bring to this side, U square plus, what do you get now here? 2as. So V square is equal to U square plus 2as. So this is the derivation of third kinematic equation by using VT graph, right? So by using VT graph, we have derived V square is equal to U square plus 2as. This is one of the important derivation. Derive V square is equal to U square plus 2as using VT graph. And we need to make use of VT graph, draw the VT graph. By seeing VT graph, you need to write the derivation, right? So this is how we derived kinematic equations using VT graph. Thank you.